The ongoing development and testing of the J-50 represent a methodical and technologically ambitious endeavor to create a sixth-generation air combat platform, moving beyond incremental improvements to establish a new paradigm in aerial warfare capabilities. The program has progressed through a series of structured and increasingly complex test flights, each designed to validate a specific subset of the aircraft's revolutionary design features and its integrated systems. The most recent flight tests indicate a critical transition in the program's life cycle, moving from the initial phase of demonstrating basic airworthiness and fundamental stability into a more advanced stage of evaluating its full performance envelope. This involves pushing the aircraft to its operational limits in speed, altitude, and maneuverability to gather critical data on structural integrity, thermal management under sustained supersonic flight, and the reliability of its propulsion systems. Furthermore, these tests are crucial for refining the complex flight control software that manages the aircraft's unconventional, unstable tailless design, ensuring predictable and safe handling across all anticipated flight conditions. The removal of temporary external instrumentation, such as flight test booms, from the prototypes is a clear indicator of this progression, signifying that the program is now relying more on internal data systems and is focusing on validating its stealth characteristics, sensor performance, and weapons integration in a configuration that closely resembles a future operational aircraft. The fundamental architectural philosophy of the J-50 is rooted in achieving a quantum leap in survivability and penetrative capability through its radical airframe configuration. The most visually distinctive feature is its complete lack of vertical and horizontal tail surfaces, a design known as a tailless or flying wing configuration. This is not merely an aesthetic choice but a deliberate and calculated engineering decision to minimize the aircraft's radar cross-section to an unprecedented degree. Vertical tails are particularly susceptible to radar detection from a wide range of angles, and their removal, combined with the extensive use of blended body lines and leading-edge sweep, results in an airframe that scatters radar energy far less effectively than any preceding generation of fighter. This design aims to achieve what is termed wideband stealth, meaning it is effective against a broad spectrum of radar frequencies, from the lower bands used by early warning systems to the higher bands used by fire control radars on enemy aircraft and surface-to-air missiles. This significantly complicates the detection, tracking, and targeting processes for adversarial air defense networks. The primary engineering challenge of a tailless design is maintaining stable and controllable flight without the conventional control surfaces that provide yaw, pitch, and roll authority. The J-50 addresses this through a revolutionary flight control system that utilizes active, swiveling wingtips. These are not simple flaps or ailerons but entire sections of the wingtip that can articulate and move independently. Through complex, computer-coordinated movements, these swiveling wingtips generate the differential drag and lift forces required to control the aircraft's attitude in all three axes. They effectively combine the functions of ailerons for roll, elevators for pitch, and a rudder for yaw into a single, integrated system. This approach is mechanically complex but offers immense advantages. It completely eliminates the radar reflective gaps, hinges, and actuator fairings associated with traditional control surfaces, thereby preserving the aircraft's pristine stealth profile. Aerodynamically, the removal of the tail and the use of this integrated control system lead to a dramatic reduction in overall drag. This translates directly into enhanced fuel efficiency, which extends the aircraft's unrefueled range and loiter time on station. It also contributes to a higher theoretical maximum speed and improved acceleration for a given level of engine thrust. The propulsion system is based on two next-generation, low-bypass turbofan engines, which are equipped with two-dimensional thrust vectoring nozzles. These nozzles can deflect the engine exhaust stream up and down, providing a powerful form of direct force control. This capability grants the aircraft exceptional agility, particularly at high angles of attack and low airspeeds where conventional aerodynamic controls become ineffective. The thrust vectoring works in a deeply integrated, synergistic manner with the swiveling wingtips. A highly sophisticated and redundant flight control computer continuously blends inputs from both the aerodynamic control surfaces and the propulsive control systems to provide the pilot with seamless and intuitive handling characteristics, even during the most demanding combat maneuvers. A critical performance metric enabled by the combination of this advanced airframe and powerful engines is sustained supercruise. This is the ability to maintain supersonic flight without the use of fuel-intensive afterburners. This capability is a monumental tactical advantage. It allows the J-50 to rapidly traverse large distances, enter and exit contested airspace quickly, and conduct supersonic intercepts while conserving vast quantities of fuel. This extended range and persistence, combined with a significantly reduced infrared signature, as the afterburner's extremely hot and visible plume is not used, make the aircraft a far more elusive and enduring threat. The engine air inlets are of a diverterless supersonic design, which uses a carefully contoured three-dimensional bump on the intake to manage the supersonic airflow and prevent the slow-moving, turbulent boundary layer air from entering the engine. This design is inherently stealthier, lighter, and more reliable than previous generations of intakes that required complex moving ramps and boundary layer diverter plates, all of which created radar reflective cavities and edges. The integration of sensors and avionics is executed with a foundational emphasis on minimizing all detectable emissions and physical apertures, adhering to the principle of first look, first shot, first kill. A key feature is an electro-optical targeting system that is fully conformal and seamlessly integrated into the aircraft's nose structure. This system operates entirely passively, using high-resolution infrared search and track capabilities to detect, track, and engage targets without emitting any detectable radar energy. This allows the J-50 to operate in a stealthy listen-only mode, targeting adversaries who are actively using their radars and thereby revealing their own position. To maintain its low observable signature, all weapons and ordnance are carried internally within shielded weapons bays. These bays are engineered with rapid-acting doors and advanced ejection launch systems to deploy missiles and precision-guided munitions in a fraction of a second, minimizing the time the bay is open and its disruptive effect on the aircraft's radar cross-section. The cockpit is configured for a single pilot, a decision that is only feasible through an unprecedented level of automation, sensor fusion, and artificial intelligence assistance. The avionics architecture is designed around an open systems concept, likely fusing data from a distributed aperture system, a network of infrared sensors placed around the airframe, providing a seamless, 360-degree spherical view of the battlespace, with data from its active electronically scanned array radar and electronic warfare systems. This fused data is presented to the pilot through a highly intuitive human-machine interface, potentially featuring large area displays and augmented reality projections. The onboard AI manages routine tasks such as systems monitoring, threat prioritization, countermeasures deployment, and network management, drastically reducing the pilot's cognitive workload and enabling effective command in the intensely complex and time-critical environment of modern beyond visual range combat. The future trajectory and strategic purpose of the J-50 program position it as the vanguard of a new generation of air power. The accelerated and parallel development of multiple prototypes indicates a concerted national effort to field this capability on a compressed timeline. The aircraft is not conceived as a standalone platform but as a key node, a premier shooter and sensor, within a larger, resilient, and networked combat system often described as a combat cloud. In this role, it would share data in real time with other J-50s, with other platforms like the larger J-36, with unmanned loyal wingman aircraft, with ground-based command and control, and with space-based assets. This networking creates a synergistic effect where the sum of the force's capability is far greater than its individual parts. A J-50 could engage a target based on tracking data provided by another platform that it itself cannot yet see. Its intended primary role is that of an air dominance and deep penetration platform, designed to neutralize an adversary's most advanced aircraft and dismantle their integrated air defense systems from the first hours of a conflict. The program's rapid progression suggests a strategic aim to achieve an initial operational capability within the current decade, with the objective of securing a decisive and sustained technological advantage in the high-threat operational environments of the future.